All right, what's the value of this integral here? You can do this the hard way, or you can use the fact that we've already proven that eigenfunctions of a Hermitian operator are non-degenerate eigenfunctions are orthonormal, right? And what do we have basically here? This is x of x for n equals 3, right? And this is y of y for n equal, this is n sub x equals 3, n sub y equals what for this one? 4. Or you can say this is the 3, 4 eigenfunction. You can call this psi 3, 4. N sub x equals 3, n sub y equals 4. So what is this number equal to? This is basically psi 3, 4 absolute value squared. If you integrate that over all possible values of x and y, so you're integrating over d tau, that's equal to, that's just the probability of finding it between 0 and L1 and x equals 0 and x equals L1 and between y equals 0 and y equals L1. What's the probability of finding the particle in the box? 1. We have an orthonormal set. Our wave functions are normalized, right? So integral of psi squared d tau is going to be equal to 1. How about this integral? Psi 1 to psi 2 1 in bracket notation. How would you expand this? This is going to be a long one, huh? So integral from dx from 0 to L1 dy, from 0 to L2. What's psi 1 to? You have to put a star for that one, and then you have psi 2 1 over here. So what's psi 1 to? It's going to be square root of 2 over L1 sine 1 pi x over L1 times square root of 2 over L2 sine 2 pi x over L2. So that thing goes in here, and something else goes in here. I'm sorry, this should be pi y. And over here, you're going to have what? Square root of 2 over L1 sine n sub x. What's our n sub x for this case? It's 2, right? So 2 pi x over L1 times square root of 2 over L2 times sine of 1 pi y over L2. And that goes in there. And when you integrate that, what do you get? You have an orthonormal set. If you did this the hard way, you get the same answer. And what's the answer? 0. Okay. So what would be your integral if you wanted to calculate the average y coordinate of your particle? Integral of y times, this is going to be psi y operator, which is just a multiplicative operator, y psi, right, in bracket notation. So this is going to be y times, you write your psi there, right? Okay, so since we didn't specify what it is, you can just say psi squared dy from y equals 0 to L2, and then you integrate over dx from x equals 0 to L1. Okay. What do you think that number is going to be based on the symmetry of the function? That's the average location of the particle along the y-axis. It's going to be L2 over 2. In fact, the x component here, the x factor is just going to factor out over here, and this part will just come out to be 1. So you'll basically get the same integral you did when you did the one-dimensional problem. Same value. How do you get the average value of the momentum? Integral of psi. What's the operator for momentum? H bar over I. Partial derivative with respect to x of psi dx from 0 to L1, and then you integrate over dy over y from 0 to L2.